So we will go through this digital twin system we built for DEMOSAT. First, we will go through the architecture presentation of the system. And then we will highlight some of the results we got from the model measure comparison study we performed. I believe this is quite a unique study because we compare for several hundred of hours the model versus the sensors, and well, in public literature, this doesn't exist. So, so we base our digital twin architecture around the simulation model of the turbine, so the global model. Manuel started to introduce you the system, and here are some description of the model itself. So for mooring lines, we have a lump mass element. For hydrodynamic, we have an hydrodynamic database from potential theory. On the structure side, we have a rigid body floater and beam elements for both tower and blades. And then for each simulation we run, we need to input some wave and current condition. We input as well a wind field. And for each sea state, we can tune some quadratic damping coefficient for additional Morrison element to complement the potential theory. So this model was calibrated over the years during wave basin campaigns, but still you have some scaling challenges, especially because you need to scale both hydrodynamic and aerodynamic, and here we kind of check if the assumptions made during basin test are good or valid. So here is an overview of the process we used to compare model versus sensors. So first we automated all the process, and first we recover some sensors data. So weather forecast as a backup, but also in situ measurements for wave, wind, current, SCADA data from the turbines and other sensors. And once we get the sensors data, we can run some simulations. So we run one simulation per hour, and we perform first pre-processing, then we run the simulation, and at the end of the running of the simulation, we have some outputs that we see as virtual sensors. So then at this step here, we transform both physical sensors and virtual sensors using the same routine, the same architecture, which allow us to transform in a unified format all the sensors in a database. So once we get that, it's quite easy to compare and to display the information for comparison. A very quick sensor description. We have some waveboy data for wave, wind speed, and current. We also have SciTech, which provided us for a limited SCADA data dataset with 20 channels at 1 Hertz. So we have about 400 hours of that data. Once we get the data, we can first pre-process the wind field. So you can see that on the right here, we have the 1 Hertz wind speed and direction at the nacelle, and with STURBSIM we compute complete wind fields which match the anemometer values. So we input and force the 1 Hertz measurements of wind into the software, and also we force at each beginning of the simulation the floater and the heading and the nacelle heading to match it better with a measurement. This is very important, especially when you have, for example, low wind, and several headings can come here. Okay. So after the simulation is run, we have some simulation outputs. We have some raw data files from sensors. And all those files can contain erroneous data, missing values, missing files. So, and we need to ingest this in a controlled manner. So, what we performed is that we defined kind of abstraction on the sensor, and all the sensors have the same architectures. So we have a unified naming scheme, unified unit and reference frame, and all the information from the channels are included within one file. And so we import the raw data and ingest it, transform it to a unified data, and by doing so we can perform some first data cleaning. So we can interpolate missing values, we can check out of range data if they are above predefined thresholds, and to monitor this process, we developed a graphical user interface to see whether each step is performing okay, and we track all the errors for each channels, each hours of simulation in files, and we have a synthetic display of that information. So to conclude on this architecture, first architecture presentation, we have a global process. This is kind of ready to go off the shelf to be adapted to other turbines or even other at-sea structures, I mean non-floating ones. We can switch from a simulation software to another quite quickly. And we can also adapt to a lot of sensors kind. Okay, so now you have an understanding of the digital twin architecture we did set up. I will present you some results of the comparisons between measurements and model we performed. So as I said, it's quite unique because there is a lot of hours compared, and if you have a look at literature, usually they compare one storm, one let's say mild condition, and that's it. So 2 to 10 maybe seed states, and we say okay, we're all good to go with the model, but probably it's it's a bit more complicated than that. So that's what we wanted to check. And so we ran for several hours the simulations. All this was running automatically. Each point you have here on the graph is for 1 hour simulation at 5 hertz. And so by doing so, we can do both subset some selection to compare the model with good data set, but we can also identify outliers in the model measurements, and there is a lot of knowledge to take that from this identification. Well, to compare model and measurements, we will focus on one subset of our dataset, and we will only consider simulations when we have all the sensors data. So, I mean, anemometer at 1 Hertz on the turbine, 1 hour statistics from Waveboy, 1 hour statistics from current. As you can see, because we don't have a very, very extensive data set, but maybe it will come later on, we are still in mild conditions. So all what I present is below 2.5 HS. Well, to compare model and measurements for some degrees of freedom, we can directly have a look at time series. And here is an example of a full afternoon. On the top here, you can see the floater heading, and in blue, you have the measurements of the heading of the floater. And in orange, you have the behavior of the floater in the model. We choose to illustrate this dataset because you have a big shift in wind direction and also in wind speed. And you can see that, yeah, in less than about 1 hour, we have 80 degrees of difference in the wind. And along the way, the model is following it quite smoothly. This is thanks to both to initiating the floater heading. You can see here that at very low speed, there was on this SPM there was several positions maybe possible in static, but we initiate at the beginning of the simulation the heading, which match good measurements and the simulation. And then when the wind is increasing, the floater is following the measurements. Well, we still have some improvements to be made here. Maybe a finer current resolution would help to model the floater heading. For other degrees of freedom, like pitch, roll, and eve, we cannot directly look and compare point by point the time series because we don't have the wave elevation at the specific point of the demosat. And so we represent the wave as a statistically representative wave conditions. So that means that we need to have a statistical approach to compare measurements and simulation. So what we did define several metrics for comparison, and on a 1 hour time series, you can see sensor and measurements on this graph. We compute the mean, we compute the standard deviation, we can also compute the area of the power spectral density. An interesting trick here is that you can choose the periods you are interested at. And then we can actually compare simulation and measurements. When we want to get ideas of the accuracy of the model, we remove the outliers and we remove the fifth and the 95 percentile. But we'll see later that this is where also we get some interesting informations. So as a result of our study, we get some metrics for model measurement accuracy, for model accuracy. And we can see that in average for pitch, eve, and roll, we are quite, the model is quite accurate. It's a bit less true on the heading, while we have a mean error of heading, which is rather good. On some hours, we have some inconsistencies, and we can, I believe, still decrease this value later on. We also had a look at natural frequencies to compare model measurements, and well, we calculate the power spectra from simulation, from measurements, and then we identify the differences. So relative error, let's say, are within expectations. Okay. We also had a look at environmental influence, environmental factor influence on the accuracy. And for most of the degrees of freedom, the error is increasing in absolute terms when the C-state is increasing. Interestingly, the pitch degrees of freedom is more accurate when the C-state increase. Okay. Well, as I said, this accuracy exercise allows to this accuracy exercise allows to get information and trust to replace some sensors with the model. Well, maybe the most important information lies in outlier studies. And now I will present you one of the case we did investigate, where we observe an outlier between simulations and measurements. So basically, this is a print screen of our graphical interface. You can see on the bottom, on the top, the environmental conditions endured by the structure, and here how the model and the measurements are matching. So at 7 o'clock, you can see there is a mismatch, while at 9 o'clock, you can see there is a good match. And when you observe the peak period, you can see there is like a strange behavior of the waves there, when the waves are switching between 12 seconds to 6 and then 13. Well, because this looks strange, we had a look at the wave conditions and especially wave buoy measurements. And what appears is that, well, in CIMA software, we used a simple Dunn trap spectrum. And in fact, this C-state is not the most common in BMAP, but you had two peaks on the wave spectrum. So what we did, we reprocessed the wave buoy accelerations and computed a 24 directional spectra and inputted that into CIMA software. And the outcomes is that, well, we match with a very better precision the Eve. So here you can see the power spectral density for measurements here in blue. In orange, it is the original PSD with very low energy. And in green, it is the results of the simulation after we modified the spectrum. So it's not a perfect match. We still have a slight shift in Eve natural period and also in energy, but nothing to compare with the beginning. We can also have a look at the pitch, and it also improve the modelization for pitch on this specific C-state. We can see that now we model the two wave peaks. We have a two peak response as for the waves here around the same frequencies. And also the pitch movements reduced. So still in blue, it's the measurements. In orange, it's the initial simulation, and in green, the modified one. Yeah, so we can see that even in the natural frequency response, there is a slight improvement of the model. Well, as a conclusion, we have a fully automated process to make operational simulations. Operational simulations allow us to detect quite easily anomalies. And if you think about Adrien's presentation, there are quite a lot of techniques that we can apply to detect anomalies, interestingly. And then those anomaly detection can allow for investigation with design teams. So more than bringing trust in the model, we will improve the design routing. You can improve the design process of your prototypes. For the model validation, overall, we get good fidelity of the model if you forget about outliers, and we have some still enhancement point observed. And for future developments, for sure, we are interested to apply this to other structures, to apply this framework to other structures. We want to, and with SciTech, we want to investigate other outliers. We will implement the refined wave modeling. And yeah, I just wanted you to be aware that thanks to the simulation running in parallel of sensors, you have access to a lot of virtual sensors. And for example, here, you can see rainflow counting on mooring lines, tension for the range of for the simulation which run. So this is just to highlight that yeah, because you have the model, you can have access to a lot of virtual sensors, and you can have a clue on the precision of those estimations thanks to sensor measuring points and comparisons point.